So, my weather app says there's a 70% chance of rain tomorrow.
Okay, then.
Well, I'm staring out the window right now, and there's not a single cloud in the sky. It is perfectly clear. So I'm sitting here wondering what that 70 actually means.
Right. It means tomorrow's weather has a specific number attached to it. The probability of rain equals zero point 0.7.
Yeah.
That's not just like a meteorologist's gut feeling. It's a system that assigns a numerical value to an event based on very rigid rules.
But why zero point 0.7? I mean, why not 90 or why not 1.2 for that matter?
Because the underlying math has strict boundaries. And understanding those boundaries is really how you quantify certainty.
Okay, so in our previous deep dives, we did establish a common language for this.
We did, yeah.
We know how to map out a sample space, which is just a list of every possible outcome of a random experiment. We know how to group those outcomes into events.
Right, and we even developed the counting techniques to figure out how many outcomes are sitting inside a given event.
Exactly. So we have the structure and we have the counting tools.
But what we need now is the actual number. We need a function, which we usually just call p, that takes an event and returns its probability.
So our mission today for you listening is to build that function so it satisfies two specific axioms.
Right. But before we do, I want to go back to your question about the weather app.
About why the probability can't be 1.2 or negative.
Yeah, exactly. That constraint is actually the foundational setup of the function itself. Before we even get to the axioms, we define the function p so that it only returns a value in the range of 0 to 1, inclusive.
So no negatives and nothing above 1.
Right. A probability of 1.2 is simply forbidden by construction. It's not a third axiom, it's just the environment we operate in.
Which makes intuitive sense. I mean, if 0 means impossible and 1 means absolutely certain, you can't be more than absolutely certain. It would break the logic.
Precisely. So from that 0 to 1 range, we introduce our two axioms. Axiom 1 is very straightforward. It states that the probability of the whole sample space is 1, and the probability of the empty set is 0.
Okay, so the whole sample space covers every single thing that could possibly happen in our random experiment.
Right.
So by definition, something in that space must happen.
Yes, it has to. So it gets a 1. And the empty set covers nothing at all, so it naturally gets a 0.
Makes sense.
Axiom 2 deals with how we combine things. It says that if two events are disjoint, meaning they cannot possibly happen at the same time, then the probability of A or B is simply the sum of their individual probabilities.
So if they do not overlap at all, you just add them together.
Yes. And what is really fascinating about this framework is that every calculation you perform, every complex predictive model you might encounter later on, ultimately flows from just those two axioms and the 0 to 1 constraint.
That's the entire foundation.
That is it.
Okay, but if that is the foundation, how do we actually go about building this function on a finite sample space? Like, we need a way to assign the actual numbers.
Well, we assign a weight to each possible outcome.
Okay.
The only requirements for these weights are that they must be non-negative, and if you add up the weights of every single outcome in the sample space, they have to sum to exactly 1.
All right, so if we think about a very simple weather forecast for tomorrow, we might have a 3-outcome model, right? Say sun, cloud, and rain.
Sure.
The forecasters look at their atmospheric data, and they assign a weight of 0.5 to sun, 0.3 to cloud, and 0.2 to rain.
And you can immediately check if that's valid. 0.5 plus 0.3 plus 0.2 equals 1.
Right.
The weights sum perfectly.
So if I want to find the probability of a broader event, say the event is cloudy or rainy, I just look at the outcomes inside that event and add up their weights.
Exactly.
So 0.3 for cloud plus 0.2 for rain. The probability is 0.5.
That is the complete mechanism for finite sample spaces. The probability of an event simply equals the sum of the weights of the outcomes it contains.
That seems almost too easy when the weights are just handed to you like that.
It is straightforward, yeah.
But I'm guessing it gets more interesting when we look at systems where the weights are perfectly balanced. What happens when every outcome has the exact same weight?
That's a very common special case.
Yeah.
Think about a fair coin or a well-shuffled deck of cards.
Okay.
When every outcome in a finite sample space shares the same weight, that weight is simply 1 divided by the total number of outcomes.
Right.
In that scenario, the probability of an event becomes size of E over size of S.
Favorable outcomes over total possible outcomes.
Exactly. When outcomes are equally likely, Computing a probability stops being about assigning weights, and it turns entirely into a counting problem.
Ah, which is why those permutation and combination tools we talked about before are so vital.
Yes, they do the heavy lifting here.
Let's actually test this out with a counting exercise we looked at recently, just to ground it for you listening. We were building 4-digit numbers from a specific set of 6 digits.
Oh, right. The set was 0, 1, 2, 5, 6, and 9.
Yeah. And the only rule was that the first digit could not be 0.
So we used the multiplication rule for that. Since the first slot cannot be 0, it has 5 choices.
Right.
The remaining 3 slots each have 6 choices, because we can reuse digits. So 5 times 6 times 6 times 6 gave us a total sample space size of S of 1,080.
So there are 1,080 total numbers we could possibly build.
Yes.
If we assume each of those numbers is equally likely to be drawn from a hat, what is the probability that the number we draw is even?
Well, we just need to find the size of our event E.
Okay.
A number is even if and only if its last digit is even. If we look at our available digits as 0, 1, 2, 5, 6, 9, the even ones are 0, 2, and 6.
So the last digit has to be a 0, a 2, or a 6. That locks in 3 choices for the final slot of our 4-digit number.
Right. And the other slots operate under the exact same constraints as before.
So the first slot still has 5 choices, because we cannot start with a 0.
Yep.
The second slot has 6 choices. The third slot has 6 choices. The only difference is that our new final slot is restricted to 3 choices.
So you multiply those. 5 times 6 times 6 times 3.
Which comes out to exactly 540.
Right. So size of E over size of S is 540 over 1,080.
Oh, nice.
Which simplifies beautifully to exactly 1/2.
Half of the numbers are even, which makes intuitive sense when you step back and look at the setup. Our original set of 6 digits had 3 even numbers and 3 odd numbers.
Exactly.
The entire number being even or odd hinges entirely on that last slot, and that slot is split evenly, 50-50.
It's a clean result, and it really proved how those basic counting tools directly hand you probabilities when your outcomes are equally likely.
Okay, so that works perfectly for distinct countable outcomes like picking digits or rolling dice. But what happens when the sample space is continuous? Like, imagine picking a random point on a map. Counting goes completely out the window because there are infinite points. How do you find favorable over total when both numbers are infinity?
You transition from counting discrete things to measuring space.
Measuring space.
Yeah. When the sample space is a two-dimensional region instead of a finite list, the equally likely concept translates to equal area.
Right.
So the probability of an event becomes the area of the event divided by the total area of the sample space.
Let's visualize that. Imagine throwing a single dart at a square target on the wall. Let's say it's a unit square, meaning it's exactly 1 foot wide and 1 foot tall.
Okay.
The dart is guaranteed to hit the square somewhere, and it's equally likely to land anywhere. So our sample space is that entire 1 by 1 square.
And because it's a unit square, the total area is simply 1 square foot. Size of S is 1.
Now we define our event. We want the probability that the dart lands below the line y equals 1/2 minus x.
Okay, if you draw that line on the target, y equals 1/2 minus x, it cuts diagonally across the bottom left corner of the square.
Yeah.
The region below that line forms a small right triangle. Both the vertical leg and the horizontal leg of that triangle are exactly 1/2 of a foot in length.
Right, and basic geometry dictates that the area of a right triangle is 1/2 times base times height.
Exactly.
So 1/2 times 1/2 times 1/2. That equals 1/8.
So the area of our event is 1/8. The total area of the target is 1.
Right.
So the probability of the dart landing in that specific corner is 1/8 over 1. The probability is 1/8.
That's really elegant. The logic of favorable over total scales perfectly from raw counts to physical areas.
It does. It's the exact same underlying concept.
Okay, but this brings up an interesting complication. We've been looking at isolated events, or events that are completely separated. But earlier, when you mentioned Axiom 2, you specifically said it applies to disjoint events.
I did, yeah.
What happens when events A and B are not disjoint? What if they overlap?
That's where the naive math breaks down. The instinct is to simply add the probability of A and the probability of B.
Right, just sum them up.
But if they overlap, adding them blindly results in double counting.
Let me try to picture this. Picture a stage with 2 overlapping spotlights. Spotlight A is casting a red circle of light, and Spotlight B is casting a blue circle of light right next to it.
Okay, good visual.
But they are positioned so that they cross over each other in the middle.
Right. That shape in the middle, the lens where the red and blue mix, is getting hit by both lights.
Yeah.
If you simply measure the total area of the red circle and add the total area of the blue circle, you've counted that middle section twice.
So if we want to know the total area of the stage that is illuminated to get the correct number, we have to subtract that overlapping section once.
Exactly. This correction gives us the additive rule. Formally, for any two events A and B, the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B.
Let's apply this to a real scenario so you can see how it works. Picture yourself in a small town that has exactly 100 adults.
Okay.
60 of those adults have a driver's license, 40 of them have a passport, and 25 of them happen to have both a license and a passport.
Right, so we have an overlap.
Yeah.
If we want to find the probability that a randomly selected adult in this town has at least one of those two documents, either a license, a passport, or both, we need the additive rule.
Because if we just added 60 and 40, we'd get 100, which implies everyone has one, but that's double counting the people with both.
Exactly. We take the 60 with a license, add the 40 with a passport, and then we must subtract the 25 who have both.
60 plus 40 is 100, minus 25 gives us 75.
So 75 out of 100 adults, the probability is 0.75.
The subtraction of 25 is purely the mathematical correction to make sure we don't count those particular people twice.
Yes, and this actually connects directly back to our earlier discussions about mutually exclusive events.
Oh, from week 1.
Right. If two events are mutually exclusive, it means they share no outcomes whatsoever. They cannot occur at the same time.
So they're completely separate circles of light on the stage.
Exactly. And if they share no outcomes, the overlap is 0. The term we subtract at the end of the additive rule just vanishes.
Which means if A and B are mutually exclusive, the probability of A or B is simply the probability of A plus the probability of B. No subtraction is required.
A simple die roll illustrates this perfectly. What is the probability of rolling a 1 or a 2?
Well, the probability of rolling a 1 is 1/6.
Right.
The probability of rolling a 2 is 1/6.
And because it is physically impossible to roll a 1 and a 2 on a single die at the exact same time, they are mutually exclusive. We simply add them.
1/6 plus 1/6 equals 2/6. That simplifies to 1/3. We don't have to worry about correcting for an overlap because an overlap does not exist.
Mutually exclusive is a powerful property.
Yeah.
But there is a related concept that is even stronger, the complement.
Okay, let's define that. Two events are complements if they have no overlap, and together, they completely fill up the entire sample space.
Yes, it's event A and absolutely everything that is not event A. Because they cover the entire space and do not overlap at all, their probabilities must add up to exactly 1.
That makes sense?
This gives us the complement rule, which says A complement equals 1 minus the probability of A.
This takes me right back to the weather app scene from the start of our conversation, a 0.70 chance of rain.
Right. If the probability of rain is 0.70, then the probability of no rain is simply 1 minus 0.70.
Which is 0.30.
Exactly.
It's a 30% chance of no rain. It is the exact same forecast, just observed from the other side of the mirror.
For a binary event like rain or no rain, flipping the perspective might seem a bit trivial, but the complement rule is actually one of the highest leverage tricks in all of probability.
Really? Why is that?
It's particularly useful because of the at least one scenario.
Ah, walk through that logic. Why does the phrase at least one signal that we should be using the complement rule?
Well, whenever a system requires you to find the probability of at least one thing happening over multiple trials, calculating it directly is an absolute nightmare.
Okay, let's set up an example. Suppose we roll a fair die 4 times in a row.
Okay.
We want to find the probability of getting at least 1/6 somewhere in those 4 rolls.
Think about what it takes to solve that the direct way. You have to break the problem into distinct cases. You have to calculate the probability of rolling exactly 1/6.
Okay.
Then you have to calculate the probability of rolling exactly 2 6s, then exactly 3, then exactly 4.
Wow.
And once you have the math for all 4 of those separate cases, you have to sum them together.
That is an incredible amount of tedious calculation, and honestly, a lot of places to make a simple arithmetic mistake.
It is. But if we use the complement trick, the entire problem just collapses.
Okay.
Let A be the event at least 1/6. What is a complement?
The exact opposite of getting at least 1/6. Well, it would be getting absolutely no 6s at all across the 4 rolls.
Precisely. We just need to find the probability of getting 0 sixes. On any single roll, the chance of not getting a 6 is 5 out of 6.
Because there are 4 independent rolls in a row, we multiply that probability out. 5/6 times 5/6 times 5/6 times 5/6.
Which is written as 5/6 to the 4th. If you calculate that, 5 to the 4th is 625. 6 to the 4th is 1,296.
So the probability of getting absolutely no 6s is 625 over 1296.
Right.
Let me pause here to make sure this lands for you listening. We originally wanted the probability of at least 1 6. Instead, we found the probability of 0 sixes. To get our final answer, we just subtract that fraction from 1.
Exactly. The probability of at least 1 6 equals 1 minus 625 over 1296.
Which comes out to 671 over 1296. If you divide that out, it is roughly 0.52, a 52% chance.
We replaced 4 complicated mathematical cases with 1 short product and a single subtraction.
That is incredibly efficient.
Yeah, when you encounter at least one scenario, reaching for the complement rule will save you a tremendous amount of time and effort.
So let's summarize the ground we have covered today. We started with the 2 foundational axioms: probabilities sum to 1 and disjoint events add.
Right.
We looked at how to assign weights to discrete outcomes, and we used the equally likely formula favorable over total to connect probability straight back to our counting techniques.
Yes, and from there, we extended that favorable over total logic to continuous sample spaces using area ratios,
And then we mapped out the additive rule for overlapping events.
which logically leads right into our 2 corollaries.
Yeah.
Mutually exclusive events, where the overlap simply vanishes, and the complement rule, which gives us that massive shortcut for at least 1 problems.
That establishes the rules of the game pretty well. What are we exploring in our next deep dive?
Next time, we move into conditional probability. We will examine how a probability changes when you learn a new piece of information mid-experiment. We will define independence, which is what it means mathematically when learning about event B tells you absolutely nothing about event A.
Oh, that sounds really interesting.
Yeah, and we will also introduce the product and chain rules.
Perfect. But before we wrap up, I want to leave you with one final thought. At the very beginning, I was looking at my weather app, confused about a 70% chance of rain while staring at a clear blue sky.
And we walk through how that 0.70 isn't just a guess. It is a number bound by the rigid mathematical rules we covered today. The axioms, the weights, the complement rule, the entire system has to add up perfectly.
You now know the strict rules that a percentage on a weather app or a news poll or a financial model must follow once the system is set up and running.
Right.
But it begs a rather crucial question for you to mull over. The math only works seamlessly after the weights are assigned. So how did the forecasters define their sample space and decide on those initial weights in the first place?